We're going to talk about normal distribution today, and so we're going to start with the what is it. If you take a large sample of measurements from a continuous random variable, in a population, a histogram of this data will look bell-shaped. The probability distribution curve for these data can be approximated using a formula for the normal distribution. Two pieces of information are required by the formula: the population mean and the population standard deviation. So now we're going to look at some notation. And so this fancy looking M is a mu, and that's our population mean. And then right below it we have our sigma there, which is our population standard deviation. And then below that we have x bar, which is our sample mean. And then below that we have S, which is our sample standard deviation. And we're going to go to the bottom left, where we're going to talk about our empirical rule. And so most of our data is near the middle, and there's less data as you move away from the middle towards the tail. And so 68% of the data are within one standard deviation of the mean. So that means that from here to here is 68% of our data. And then 95% of our data are within two standard deviations of the mean. And so that means that from here to here is 95% of our data. And then the last is that 99.7% of the data are within three standard deviations of the mean. And so that means that from here to here is 99.7% of our data. So now we're going to continue to the right, where we're going to talk about our curve. And so when you have a normal curve like this, your mean, your median, and your mode are all at the very top of your curve. Each tail extends to infinity, and it's bell-shaped. This curve is symmetric about the mean. The shape is determined by two parameters. Those parameters are your population mean, where the middle is, and your population standard deviation, which is how wide and tall it is. So we often don't know these parameters. So we have to estimate them using x bar, which is our sample mean, and S, which is our sample standard deviation. And this is ideally from a sample that is larger than 30. So on the next page, so the area under the curve represents the probability of all possible outcomes. The total area under the curve is therefore equal to 1 or 100%. We can work out the percentage of data that lie within a given range of values using the empirical rule, which was on the previous slide, a z-table, which we're not going to use that at all in this class, and a statistical software package, which in this class we're going to use our calculator. So then z-scores, a z-score is a numerical value that tells you how far a value x is from the mean. It measures distance in terms of standard deviation. So for example, a z-score of 2 means that the value x is 2 standard deviations above the mean. So if we had a z-score of -2, that would mean that we're 2 standard deviations below the mean. And so then you have z-scores are used to calculate these percentages, and a z-score is calculated using the following formula, where this is a z. It didn't print very well, but that is a z. And so it says z is equal to x, which is our data value that we're using, minus the mean of all of our data values, divided by the standard deviation of all of our data values. Let's go to the top right and do an example. So on a standardized exam, the scores are normally distributed with a mean of 170 and a standard deviation of 20. Find the z-score of a person who scored 140 on the exam. So we're going to say, okay, our z-score is equal to our data value of 140 minus our mean of 170 divided by our standard deviation of 20. So that gives us -30 over 20, which is -3 over 2. So our z-score is -1.5. And so that tells us that the score of 140 is 1.5 standard deviations below the mean. All right, we're going to straight down now. So just some real-world examples. So data collected on many natural phenomena such as height and weight of people have an approximate normal distribution. So these data are typically influenced by many factors, but no single factor overpowers the other.